almost. So we will now go into the localization realm, and we'll have Rodolfo Panerai talking about localization and resummation in 2D angles.
Okay, thanks. Yeah, first of all, of course, I want to thank the organizers for putting together such an amazing conference and for giving me the opportunity to present this work here. The talk is based on a paper that appeared early this year and was done in collaboration with Luca Griguolo, Jacopo Papalini, Domenico Seminara, and Ita Mariaco. So, as a means just of a motivation, let me start with a very basic observation. Of course, that the examples of interacting quantum field theories for which the full trans-series expansion or either the partition function or in general observables can be computed exactly are very rare. And typically, of course, if you can do this, it means that you can somehow solve your theory exactly. But solvability and the possibility of deriving this expansion, they don't necessarily always go hand in hand. For instance, two-dimensional Yang-Mills theory is a solvable model. It was solved like 50 years ago or so. But deriving its weak coupling expansion has proven to be surprisingly elusive, so it remained an open problem for a long time. And actually, for general gauge groups, it's still an open problem. But I want to make a few comments to maybe convince you that there is value in trying to derive this expansion, and in particular, in explicitly deriving this, we will kind of gain some understanding on the interplay between a weak coupling and a strong coupling expansion of a theory and ways to obtain one from the other. Also, of course, we are going to explore the role played by the critical points of the classical action in the result. And this is something that is specific to the Yang-Mills, but there's a paper by Witter in the early 19th in which he obtained, or at least studied the partition function of the theory using some non-abelian localization argument. And this was mainly used to infer what is the structure of the result more than to derive some explicit result. And we would like to understand this localization argument from a computational perspective. And in doing so, we will find some non-standard type of supersymmetric effective action. Okay. More, of course, but okay, this slide is just some quick recap of some main feature of 2D Yang-Mills. We consider the Euclidean theory on a compact orientable surface sigma, and the action that you write down is the one that you would write in any dimension. The action, of course, is gauge invariant, and we're going to consider for the moment any simple gauge group. And it's also, but this is a special feature of 2D, that the action is invariant under a large class of space-time symmetries. These are called area-preserving diffeomorphisms. And so the theory, as a result, becomes what is so-called as almost topological. So it depends on the background geometry in a very mild way. The only thing that the theory knows about is the total area rho of the surface sigma. Not only that, but the gauge coupling epsilon and this total area rho always appear together in the combination epsilon times rho. So you might as well just switch to units where rho is equal to 1, and so you have just one coupling that the theory depends on. So as I was saying, the theory is solvable, and one way that you can argue this, and this was done by Migdal in the 70s, is that you can formulate the theory on the lattice. So you have a discretized version of your theory, and you can think of that you want to approach the continuum limit just by refining your triangulation of your surface. But at each step, where you add more and more plaquettes, you find that the result for the partition function is the same. So in a sense, any triangulation of your surface, any discretized version of your surface will produce on the nose the result for the theory in the continuum. So the result is the following. You can write the partition function as a sum that runs over all the reducible representations of the gauge group, of what? This is the dimension of the representation raised to the power of the Euler characteristic of your surface. G is the genus. And then you have an exponential where you have the eigenvalue of the quadratic Casimir of the representation that basically plays the role of a Hamiltonian. Of course, this provides a strong coupling expansion of the theory for the simple reason that when epsilon is large, only the terms of the sum where C2 is small dominate and everything else is exponentially suppressed. Okay, this is a strong coupling. What about a weak coupling expansion of the theory? Well, as always, when you have some quantum field theory, like some Lagrangian quantum field theory, you can formulate it with a perturbative expansion in the coupling. So you pick your path integral. This is, I'm being very schematic, but basically you separate the quadratic part of the action and the so-called interactive part that you write as a power series in your gauge coupling. And then you swap the integral with a sum. And so you can express your path integral as a power series, and the coefficients of this power series are given by Gaussian integrals. Right. All right, you can do this, and then you find out that the perturbative expansion truncates in this specific example. Now, this is a bit puzzling. So what you find specifically is that up to after a certain power in epsilon, all the Feynman diagrams in your theory, they sum up to 0. However, we know that Z is not a polynomial. We had it in the previous slide. It's a sum of exponentials. So it's definitely not a polynomial. So what is going on? Okay, this is a parallel session on resurgence, so we all know what's going on. Of course, this here is not an equal sign. These are different. By power expanding, you are missing out all the non-perturbative corrections to your result. And in this case, so you should not just consider a power series, but a trans series. You have a power series, but this is nested inside a sum that here runs over the critical points of the Yang-Mills action. And 1 over epsilon behavior of this tells you that these are exponentials that are non-perturbative in nature. And what are these critical points? These critical points are unstable instantons. And so if you have used, for instance, to the U1 theory on a sphere, these are just Dirac monopoles. They are labeled by some quantized magnetic flux M that takes values in the Corot lattice of G. And I call them unstable because these are solutions of the Yang-Mills equation, but they are not necessarily local minima. They're just critical points.
Do we know the number of negative directions around each one of these solutions?
You can classify. And for the localization argument, it's crucial to actually, because each one carries a power of I, and then you have to take that into account. Right, and actually, let's come to the last slide before switching to novel results. So this is, there's an equivalent way to formulate the theory. You can formulate it by adding some auxiliary fields. So you have a scalar phi and a one-form psi that takes value, there is a fermion. So this is the path integral of this new theory, but upon integrating out the auxiliary fields, you land back exactly on the theory that you started with. But the interesting thing is that now you have supersymmetry for free. This is, you have just one supercharge, and this is the action of the supercharge on the fields. And this was the formulation of the theory that Witten started with to introduce this localization formula, which is the supersymmetric infinite dimensional version of a localization formula in symplectic geometry. The idea, I'm being very schematic here, but the idea is that the space of gauge connection on a certain principal bundle in 2D is some Kähler manifold, and gauge transformation acts symplectically. So you can use techniques from like the Dusten-Manikman formula or some non-abelian generalization of the formula to localize the path integral. And what you find is that the path integral localizes on the critical point set of the Yang-Mills action. So you have the space of all connections, but you can localize the integral on the critical point set of this function on such a space. And here I'm writing Z as a sum over the connected components of this critical point set. And you see that this is coincide exactly with our intuition that comes from the perturbative expansion. Again, we have a sum over the solutions of the Yang-Mills equation. And again, these are just the magnetic fluxes of the instantons. So the contribution from the absolute minimum is the one where M is 0, and this is the perturbative sector. And Witten told us that this computes the intersection number of the moduli space of of flat connections. And this is a polynomial, is that I was telling you the perturbative factor truncates. There's only a finite number of powers that contribute. But contributions from higher critical points instead, they are the ones where m is not 0. And they have, you can infer again from localization that they scale exactly as you would expect them to. Like with this specific exponential where we have the classical action evaluated on the instanton part. Okay, let me speed it up. Okay, maybe I will skip this and just go to few questions that we want to address. First of all, we started with this trans-series ansatz. This is an ansatz, but it seems to be confirmed by localization. The question is this correct? And if so, can we explicitly compute all the coefficients that appear here? Second question, can we compute not simply the coefficients here, but there is some version of this sum here that computes the so-called instanton contribution that comes from localization? And can we do it from localization, from a genuine localization computation? And lastly, we know that localization is a way that we can use to start from a path integral, so that we're integrating over an infinite number of degrees of freedom. But the power supersymmetry tells us that we can describe a protected subset of the theory in terms of a much simpler quantum mechanical model, some matrix models, some integral over a finite number of degrees of freedom. And can we obtain this matrix model formulation for our theory? Okay, yes?
These alphas depend on epsilon.
No, they shouldn't. Sorry, it's you're right. That's definitely a typo. Thanks, that was both. No, of course they don't. They depend on the genus G and the specific instanton sector. No, that's right. Yeah, you're absolutely right. Okay, I want to study explicitly the SU2 case. It is simple. The irreducible representation are labeled by a single positive integer. The instantons are labeled by a single non-negative integer. So this is the starting point. It's the Migdal or lattice formulation. And we want to land on something of this form. And we know that each instanton sector has to contain this exponential behavior. And when you look at this, you say, well, okay, this exponential and this exponential here, they really look like they're related by some Fourier transform, right? Of course, this is the action evaluated on the instanton that carries some magnetic flux n. Okay, so then the most obvious thing to do is to apply Poisson summation. Okay, you can apply Poisson summation. Typically, this should be a sum that goes from minus infinity to infinity, but this is an even function. So just reflect the domain of summation. You have to remove the point in 0 that does not exist, so you remove it, and this is the expression. So you start with f, which is the argument of the sum, you compute the Fourier transform, and you're done.
How do you regulate f of 0?
That's right. So you can only do it for genus 0 and genus 1. When you go to genus 2 and above, this stuff cannot be done for the single reason that, of course, you have a divergence in the origin. And the Fourier transform does not exist in the usual sense. Well, you could say that, but I don't really want the point in the origin, but you still have to, it's not part of the sum, it's fine, the sum is perfectly fine. It's that you don't know how to apply Poisson summation. You can, though, regard f as a temperate distribution, and you can use a distributional generalization of Poisson summation. So f in 0 is the integral across the whole domain of the Fourier transform. So maybe there's a way of regulating the sum and the integral, take the difference between the two, and then go to the limit in which you lift your cutoff, and then you find the result. This still doesn't work because there are subleading divergences in lambda that spoil this limit, but there's a way of making sense of this. This is called the Cesaro limit. That's why there's a C there, and there are papers in the math literature that deals with this. This is called sometimes generalized Euler-Maclaurin expansion. But anyway, without getting into the detail of this, let me tell you what the result is. So, for the 0 instanton sector, we find this expression, and this was known, and this is the only part of the result that is known, and this appeared in the paper by Witten, modulos just one of these powers. But for a generic instanton sector, this is the result that we find, that we write as, okay, this instanton, this exponential we expect, times a polynomial, plus some combination of error function -1 that has the same asymptotic behavior of this exponential times another polynomial. And the polynomial we can compute explicitly in terms of special polynomials, Hermite, generalized Laguerre, and so on and so forth. Now we are here, we want the asymptotic expansion. So we can asymptotically expand for small positive epsilon, and we can find the result of a single instanton sector in this term, in terms of the individual term that should appear in a transeries. And the coefficients we can compute exactly, and we can see that they scale as k factorial. But upon Borel summation, you can do it for any m and any g. This reproduces exactly this, of course, this function that is here. And the same technique can be applied to determine the full transeries expansion for any observable of the theory. You want correlator of Wilson loops, you want insertion of local operators, anything. This same technique can be applied, and you can generate the full transeries for anything. Okay, as a last slide, let me say something about localization, because I promised it. So again, with localization, the idea is that you're not interested in the full theory, but just the protected sector is the cohomology induced by your fermionic charge. And you can describe this by some effective action on some finite dimensional bosonic moduli. These are certain solutions of like supersymmetric configuration, essentially. And in this case, supersymmetry tells us what they are. These are the solutions of the Yang-Mills equation. So again, instantons. And for the scalar, the auxiliary scalar phi, this must be covariantly constant modes for this scalar phi. So for SU2, we have this form for the instanton and some constant mode for phi in the Cartan subalgebra of SU2. So even before attempting to do localization, we know that the result should look like something like this. Each instanton sector should appear as an integral over this constant phi naught. Then we have the exponential of the classical action evaluated on this bosonic moduli. This is the bosonic part of the action, times something which is usually called some one-loop determinant, something that captures fluctuations about this bosonic moduli, quadratic fluctuations. And in fact, people attempted this computation, and they were, I would say, partially successful with this. There is a result by Blau and Thompson in the 90s. They used the torus gauge, and this gives you some result for this one-loop determinant that, as you can see, it does not depend really on m. It only depends on phi naught. But again, it's non-integrable. Seems to have some similar pathology as we had earlier. You cannot insert delta in this integral, compute the integral, and find out what is the contribution of a single instanton. And yet, the solution must be somehow morally correct for this simple reason. If I first perform the sum over m, so I sum over all instanton sectors, move the sum inside the integral, here the only thing that depends on m is this complex exponential. I get the Dirac comb, and then I integrate over Dirac comb, but I land back exactly on the Migdal formula for the lattice. So, but this is exactly what we didn't want. We want to compute the single contribution of a single instanton sector. And I won't give you the detail of how we derive this, but we do like a bona fide localization computation, and this is the correct answer. And if you're used to localization, this might be a bit strange because this is a distribution, it's not a function. And there is no way to reproduce this result in terms of a function. The result must be a distribution. And you can also see why the result here is morally correct. Because if you are away from the origin, you can disregard the presence of the delta function, and you can also disregard the principal value prescription. You just take a certain number of derivatives of 1 over phi, and you get precisely this power here. Okay, and it's easy to check that with this specific delta, if you plug it in, you can compute the integral, and this reproduces on the nose the instanton contribution that we had earlier. All right, just a quick conclusion. We can compute the all-order transeries to the Yang-Mills, at least for certain gauge groups. For genus G greater than 2, the perturbative expansion around each SU2 instanton is asymptotic and can be obtained, for instance, from the lattice formulation, but also can be obtained from localization. And this allows us to compute the individual contribution of each instanton sector. Generalization, we have the results for other gauge groups and various observables. And maybe we can use similar ideas to understand other prescription in localization that has to do with effective actions that are meromorphic function and involve some contour prescription, maybe JK residues and so on. And lastly, generalization to all sorts of cases. Okay, I'll stop here. Thanks.
We have time for one quick question.
Let's do.
Yeah. Do you have any physical intuition for the form you get from the lattice? You have two dual representations of the same path integral. The one involving instantons has a clear physical interpretation. There was a sum over
this one.
Yeah. So.
Right. Yeah. There is definitely. So you have to start by considering the action for a single plaquette, and then you glue them together by.
I mean, what these physically could correspond to, because you have in the dual kind of representation, you have an instanton sectors which are 1 over epsilon or 1 over your coupling. And
right.
Here you have also an exponential term which is now just e to the minus epsilon. Could you interpret this as coming from some kind of dual theory?
Not directly. I mean, this one has to do. If anything, you can regard this in terms of the fact that you are considering. So if you remember the expression of the formulation of the theory as a supersymmetric theory, this is a BF theory with a quadratic potential. Mm-hmm. And this translates to the fact that you have the quadratic Casimir here and you have a positive power of epsilon. You can consider more general theories where instead of having just a trace of phi squared, you have a more general potential. Something cubic, some quartic, so on and so forth. And you see that this is epsilon and then trace phi squared. And this would reflect by the fact that you don't only have the quadratic Casimir, but you have higher Casimirs that appear there with their coupling in front. That's basically the most direct way that you can understand the contribution there.
But yeah, so there's no kind of physical, these correspond.
I mean, it's like the Hamiltonian of your theory,
okay.
And this theory is part of a family of theories where you can change the Hamiltonian by simply changing the value of the form of the invariant polynomial that you put in your potential. So it really reflects the fact that this is just quadratic in phi. This is the.
So we really have to.
But there was another question, maybe.
Sorry,
okay.
we're really out of time. Sorry, we can talk many minutes, but there's still one last coffee break to talk. Sorry.
Thanks again.